and welcome to the first in a three-part series of Tech Exchange talks titled The Move into Millimeter Wave Frequencies. I'm David Maliniak, Senior Editor of Microwaves and RF. Today I'm speaking with Giorgia Zucchelli. Giorgia is Product Manager for RF and Mixed Signal at MathWorks, about how engineers can adapt to this changing design environment. Welcome, Giorgia. Nice to see you again.
Hey, David. Thank you. Thank you very much for having me.
It's our pleasure. In this first part of the series, we're going to get an overview of topics regarding frequencies and interfering signals in wideband receivers. How do you assess the impact of these interferers, and how can you test equalization algorithms and evaluate system operability across different bandwidths? And we'll also cover some of the consequences of interfering signals, such as saturation and desensitization, and we'll look at some filtering techniques that are often used to mitigate these effects. So to get started, Giorgia, how do you determine and minimize the impact of frequency dispersion on the performance of wideband signals? And further, how do you test equalization algorithms?
So first of all, dispersion has always been there, but it's becoming more important as the bandwidth of the signals increases. And with frequencies moving into the millimeter wave range, one of the main drivers to move to the millimeter wave range is to offer larger bandwidth for the different communication systems. And now, when we operate over large bandwidth, what happens is the behavior of the transmitter or the receiver might not be flat, both in amplitude and phase. And this ultimately leads to distortion of the constellation that will look like essentially noise. The sources for dispersion are, first of all, distributed elements like transmission lines, PCBs, antennas, but even active components such as amplifiers are not flat necessarily over the bandwidth of frequencies that is under consideration. And things actually become even more complicated with antennas. In general, if you come from the sub-6 gigahertz domain, you tend to think as an antenna as a component that has a flat behavior over frequency. But with signals of bandwidth in the range of hundreds of megahertz, we're already talking about 400, 800 megahertz, up to 1 gigahertz and above. Then even antennas are not flat anymore. And then it becomes trickier to test and verify because, then what do? You go to an anechoic chamber, you have to do over-the-air testing. Things are, bottom line, it's becoming complicated. The good news is that all of the sources of dispersion are actually static, so they don't change, or they change little in time, which means that you can use static analysis tools or electromagnetic analysis to assess what are the sources of dispersion, what is, and possibly how to mitigate them. There are other sources of dispersion that are often not called out, like channels. Over the air. If you have a transmitter and receiver over the air, and especially if the transmitter and the receiver move in space, then the effects of the channel might not be constant. It might be attenuating different frequencies or different components of the signals in different ways. The good news is that essentially, the good news or the bad news, the receiver has to undo this dispersion, or this the fact that the behavior of the transmitter plus receiver plus channel is not flat, and we all have equalization algorithms embedded in the receiver to undo this dispersion. Equalizers tend to be essentially take care of a bit of everything. They don't make a distinction: is this static, is this dynamic? To do that, you need channel estimation. For this reason, actually, most communication systems use signals such as pilots that allow the estimation of the channel. And as they estimate the channel, they also estimate the sources for dispersion of the transmitter and the receiver. That's why it's very important when you assess your communication link, you actually do include an equalization algorithm to automatically correct for these impairments. So that's a long story, but essentially the sources of dispersion can be different dispersion that get embedded into the into the entire system, into the channel, we need equalization algorithms. And then how do we test the equalization algorithms? It can be done through simulation. That's a modeling and simulation is always my go-to or my first way to look into these issues. But ultimately, this can also be done through prototyping, for example, by prototyping your equalization algorithms on an FPGA and then prototype and see how it works in real life. That's, if you like, the next step or step two to test if the inversion of the channel or the inversion of the dispersion embedded by the equalization algorithm can be done, essentially.
And I wanted to ask, with artificial intelligence being such a hot topic these days, how can AI figure into that picture of test and application of these equalization algorithms?
Right. So, like I was saying before, you use pilots to estimate the channel, and then this channel needs to be inverted in order to be equalized. With the move towards millimeter wave frequencies, systems tend to become more complicated. We tend to use more antennas, and with MIMO becoming massive MIMO, essentially the problem of the inversion of the channel becomes a really large problem, numerically complicated problem. It's really hard, and it can even lead to numerical instability. In this context, AI can really help. It helps with essentially providing an alternative for channel estimation and channel inversion or channel equalization. There's an interesting trend in this context that is about the use of autoencoders. So traditionally in wireless systems, all the components or the algorithmic components of the receiver tend to be designed and optimized separately, like channel coding, modulation, equalization, synchronization. Each had its own subsystem, and each was designed and optimized separately. Autoencoders is a new trend, essentially, and they use AI to jointly optimize both transmitter and receiver as a whole. So it becomes like a big blocks. Autoencoders used to come, used to be essentially first used for image processing to reduce redundancy. In the wireless world, they're used almost reversed. They add essentially they add redundancy to estimate the channel and to estimate the entire transmitter and receiver information. And they do this using AI in an unsupervised way. So the use of AI for channel equalization and optimization is becoming really, really helping to solve this big numerical problem and go beyond just the equalization algorithm. That's an interesting trend, at least in the market.
In the outset, we've mentioned the notion of the system operating over different frequency bandwidths. How do you assess whether the system can accommodate that kind of environment?
Right. So, moving towards higher frequencies, millimeter wave, we have a huge bandwidth that's available, so it makes sense to have adaptive radios, cognitive radios that operate multiple bandwidth. And one of the greatest technology that comes to help here is radio FDM. Orthogonal frequency division multiplexing is a great technique that allows us to essentially scale up or down the bandwidth of the signal that gets used. And is very flexible to be retargeted over different frequencies, central frequencies, as well as different bandwidth. So that's one piece of technology that really help us to target these different technologies. If I read your question right, assess in the sense of how do I design a system to target multiple frequencies bandwidth, the first starting point, of course, is assess or know what are your requirements. And we always start with a link budget analysis. But given that the frequency behavior of any transmitter or receiver is not flat, this requires including algorithmic adaptability. So you need to have transmitter and receivers that are highly tunable, highly versatile. So this might mean taking advantage of digital filters that are highly reconfigurable, but also analog equalization and calibration algorithms, from AGC in the simplest way to digital predistortion for linearization. They need to be integrated. So that's why I would say that with larger bandwidth and high frequencies, there is no RF system that is just RF. Everything is digital assisted, everything is controlled, everything is tunable, and this adds a lot of complexity. And last but not least, how do you assess if the quality of what you have designed is good or not? Is, I would say, by going beyond the classic single tone or CW tone measurements. So using metrics such as EVM or SELR, broader bands measurements, and using assessing the quality of the constellation of the receivers or the received signal, that really tells you is working or not working. A CW tone gives you some information, but it doesn't give the whole picture. Again, long answer to how to go about things.
These are complicated subjects. Let's transition now over to interfering signals. How do you measure their impact on the performance of the system? And does it matter if they're in band or out of band?
Oh, right. Yes, absolutely. So again, interfering signals affect receivers. So essentially, you have a receiver, you have a radio, and then you expect to receive a piece of information, and then you have maybe another transmitter that interferes with your receiver. And unfortunately, this can be much higher in power. So what happens in the end is that your received signal will be distorted, essentially. So ultimately, you see distortion in the constellation. You will see the signal to noise ratio going up. An interfering signal will look like noise, except that it will probably be spectrally colored, but equally uncorrelated to the signal of interest. An interferer that is in band or out of band makes a huge difference, both on how you can anticipate effects as well how you can compensate for the interferer. So it's interesting because interferers is mitigation of interfering is something where you can actively do something differently from noise in a way. So out-of-band interferers are in a way easier because they're far away in frequency. You can think I can put a filter and just cut them out. This works relatively fine when you have a receiver that is supposed to work on a relatively limited bandwidth. If you know that your receiver has to work from, I don't know, 24 to 27 gigahertz, and your interfering signal comes in at 30 gigahertz or at 19 gigahertz, then you can remove it with a filter. The tricky bit here is that the filter has to be in the RF domain. Otherwise, if this interfering signal has a much higher power, then it will send your receiver into saturation, potentially. It will desensitize either the RF front end or the ADC, which means that any digital filter that you will put is, in a way, is too late. It will not help to recover the desired information. So out-of-band interferers, yes, you can remove them with filtering, but they have to be RF filters. They're often expensive, they're often bulky, and very limited tuning. In-band interferers are trickier because you cannot filter them out. But with 5G and 6G and the introduction of beamforming and MIMO or arrays of antennas with many elements has given us a new tool or an additional tool to remove interferers by simply steering a null in the direction from which the interferer is coming from. This, of course, works when the interferer and the signal of interest are coming from two different directions. So you can say, and if you have a relatively large antenna array, then you can steer the beam towards the signal of interest and steer a null towards the interferer, and that still allows you to recover information. And the other consequence of this is that you can build very large or receivers with very large bandwidth, where you can steer the beams in such a way if you have sufficient antenna elements. And then your receiver becomes essentially noise limited. So it becomes an interesting problem, because essentially you need to have ADCs with much wider dynamic range and make sure that you can recover the signal of interest. So lots of interesting technology happening here as well, and lots of new doors that get opened for interference mitigation and for the design of better receivers, essentially.
Yeah, absolutely. On the part of the actual receiver, the wideband receiver, what are the effects that these interfering signals can have? And I'm thinking in terms of things like saturation and desensitization. How do they impact the receiver?
Yeah, essentially what happens is that an interfering signal comes in straight onto the antenna. The antenna is a passive element, will let the signal go through. And then it depends a little bit what, in general, the first component that you find is a low noise amplifier. What happens is that the low noise amplifier is often designed to expect a signal, let's say, very close to noise or very low in power, and increase it by adding as little noise as possible. Now, if an interfering signal comes in and is high in power, what might happen is that our LNA saturates. And at that point in time, you're done. There is nothing you can do. I mean, once the amplifiers are saturated, all extra information that gets sent, that gets received, essentially gets lost. That's bad news, essentially, and that's why it's important to have either filters or to have either LNAs that offer a high dynamic range, or you use a null steering, like we were mentioning before. The other option is that you design a very good LNA with a very wide dynamic range, but then you hit the saturation of the ADC or the analog to digital converter. That's the other option. Then again, you need to have more bits and a wider dynamic range for the ADC. So this is where essentially building models and building simulation tools is very useful for you to know what is the limiting factor in your receiver. What is the first thing that saturates or that clips? And in often cases, having digital filters, like I would say, is too late, because everything else happens before that. A nice case, actually, that I worked on was on a simulation study where we had an altimeter radar or a radar used as an altimeter on a plane. And these radars, these altimeters, they have receivers that are ultra large in bandwidth, and they have to be ultra large in bandwidth because essentially you need to transmit and receive pulse signals, so signals with very large spectral content in terms of bandwidth. And then what can happen is that, for example, you could have a 5G signal from a base station accidentally being steered towards a plane, and that would send your altimeter receiver into saturation. So those are the type of things where essentially it's very important to have a simulation framework where you can say what is the scenario and what are the consequences of that. And we could really see with that case study that the receiver, the altimeter was giving the wrong reading once it was getting close to the ground. Just to make an example, very very fascinating, I think.
Yes. And about mitigation of interference, you've spoken earlier about filtering. What are some of the methods and techniques that are typically used for filtering interference?
Right. So we talked about analog filters or RF filters. Like I was saying before, those are the filters. Essentially, putting a filter as close as possible to your antenna. That's a good strategy, but those tend to be bulky, not very tunable either. So if you want to have an RF receiver that is agile, these filters are not a great choice. Beam steering, null steering is a far more interesting technology, but that will only work in a millimeter wave range. Because you need to have a large arrays with lots of antennas, and it's only possible to pack together lots of antennas when you operate at high frequency. You can't really do a massive MIMO system sub 6 gigahertz, because then essentially it's you will end up with carrying around a very big system with you. But the good news is that sub 6 gigahertz, you can use different type of architectures, and we've seen it coming up a lot in the recent years, the so-called RF DACs or RF ADCs, where essentially you pretty much bypass completely the entire RF front end. You have an ultra large bandwidth or super fast ADCs or DAC, and essentially enter in the digital domain right away. And essentially, this is becoming more and more applicable for sub 6 gigahertz. It requires fewer RF components or fewer components in general, and you can do all the filtering in the RF domain. So that's essentially the holy grail of the software-defined radios. So the bottom line is that depending on the frequencies and the bandwidth and the technology that you have available, there might be different choices that you can take to reduce the impact of interferers and make your radio and your receiver work.
Okay. Well, I think we pretty much covered it for now, and so we'll stop here for today. Thanks, Giorgia, for your insights into this topic. It's of great interest to our audience, of course. And everybody, please stay tuned for the next installment in this series, and there we'll discuss some of the requirements and challenges of these mmWave systems.